Okay, we are going to look at virtual work and stability next. A very important topic because it will save you time. If you understand it, it's better, cheaper, faster. Okie dokie, next slide. Now, what you've learned so far can be used on the problems that virtual work is good for. But virtual work is better, cheaper, faster. You get the information you want and ignore the rest. It's like method of sections. You find out the tension in particular beams, not everything. So that's where it's very good. So think about the three springs in the following figure with different equilibrium lengths. So you can solve it with force equilibrium, but it takes three equations and three unknowns. It's not too bad. With virtual work, one equation makes it simple. So just think about bigger problems. One equation using virtual work, many equations using other methods. That's with 1 degree of freedom, which we'll get to later. There might be 2 degrees of freedom or whatever, but nonetheless, no matter what you do, it simplifies problems. It makes getting to the answer you need quicker, better, cheaper, faster. Stability. So far, we haven't talked about stability at all. So we find an equilibrium. We don't know if it's stable. So here we have a pencil. So let's take a look at our pencil here. And it's unstable. It'll tip. You know that. It's in equilibrium. We do run all our calculations. It's in equilibrium, but it's going to fall over. It's not stable. So that's important. So try this experiment in an empty parking lot. Drive your car straight in a moderate speed, turn some amount, and let go of the steering wheel. The car will continue. It will go in the direction the rear wheels point. That's what stability is. It returns to to its original position, whatever direction the rear wheels point. Now, drive your car in reverse and try the same experiment. Turn your wheel some, let go of the steering wheel. This time the car will keep turning. It's stability. Why cars steering is always from the front. So nowadays they're experimenting with rear wheel steering. Forklifts have rear wheel steering, but it's slow enough that the driver can compensate. Rear wheel steering makes a car more maneuverable, or a forklift for that matter. Improves stability when pulling a trailer, but it's not as stable without a trailer. Here's another example of stability right here. Physicists back in the 1980s, they figured out magnetic confinement fusion, but the solution was unstable. So they built their reactors, they turned them on, they thought, oh, we got hydrogen fusion, but it didn't happen. We're still working on that. So now we need to we need to review something. Work of a force. Work done by a force. du equals force times the displacement, or the dot product of force dot differential, dr. It can be positive or negative scalar. Units are Newton meters in the metric system, or joules. Foot-pounds, second system, foot-pounds. You can think of it as the projection of the force on the same axis as the displacement vector and multiply the two together. So the projection of the force is F cosine theta, or the projection of the displacement vector on the direction of the force. And multiply it by this projection times the force. You can think of it either way. Next slide. So moments, work of a moment. A moment, recall, is force times the lever arm, and it's actually a cross product vector-wise. This is the scalar equation, and that's force perpendicular to the radius, or radius perpendicular to the force. A displacement will also do work. So we think of a body like this with a couple moment. Here's the couple moment right here. Just right there. And now you displace it DRA and DRA. So here's a parallel line. This is a parallelogram. Right here is a parallelogram. So the force times this displacement, well, you have one as a negative force and one's a positive force. And they're both parallel. And the displacements are parallel. So they're going to cancel each other out. And all you're left with is this displacement and this force, which gives you the work done right here. F equals, or du, the work, is F, the upper force, times the radius, that would be this guy right here, times d theta. So if they're both in the same sense, that is, they're both clockwise or they're both counterclockwise, the moment's positive. If they have opposite senses, one is clockwise and the other is counterclockwise. If moment is clockwise and d theta is counterclockwise, or moment is counterclockwise and d theta is clockwise, then the work is going to be zero, or less than zero, excuse me. Units are just like before, joules or foot-pounds. Next slide. Virtual work. What we do here is we pretend to do work. We move the body a tiny amount, either distance or angle, and ask how much work is done. Usually just one. We want to simplify problems. If no work is done, then the body is in equilibrium. We don't know yet if it's a stable or unstable equilibrium. We use the symbol, the lowercase Greek delta. That's this little symbol here. It's a delta again, to mean this is a virtual displacement. That's all this means. It's like a differential. That is, we're going to take the limit as it goes to zero, but the delta out in front just means it's virtual work. It's a virtual displacement. Virtual displacement here, virtual displacement angle here. In equilibrium, delta U equals zero. The virtual work equals zero. So here's a simple example. Ball on the floor, real easy. Normal force, reaction force is going up, work is going down. So we ask, what happens if we displace it just a tiny amount, delta y? And are we in equilibrium? So we set delta U equals W minus N, that's the force, times delta y. And in equilibrium, it equals zero. And of course that means W minus N halves equals 0. This is force balance, what we've learned before. We'll take this result. The result is just like we've learned, but we'll take it and apply it to more complicated problems, problems which you would have a very difficult time working force balances on, but then they fall out just like a piece of cake when you do virtual work. Next slide.